All right, this section is about the exponential growth equation and what it looks like when it's a differential equation. You studied the exponential growth equation, I assume, in advanced algebra, probably. So that's the one that looks like y equals PERT, and we're going to relate that to its differential equation. So the classic PERT situations that you talked about in intermediate algebra were bacteria growth. So you have bacteria growth. The more bacteria you have, the faster your growth rate is. And so the rate of change of bacteria is proportional to the amount of bacteria you have. Or exponential decay, radioactive decay. So you have a radioactive material. The more radioactive material you have, the faster the material decays. The rate of change is proportional to the amount. Also for compound interest. The more money you have in your bank account, the faster your bank account grows. These are all situations where the rate of change is proportional to the amount, and they're all situations which you can write as an exponential equation. In terms of a differential equation, this is what that looks like. So dy dt is going to be the rate of change over time for your amount. And that is going to be proportional to the amount of material you have. We're going to go through this kind of proof of why is this PERT from intermediate algebra class or advanced algebra class. So we're going to go through the differential equation. We're going to do our first step. We're going to separate out the variables. Go ahead and try that. So I'm going to multiply both sides by dt. And I'm going to divide both sides by y. And I'm going to do the integral of both sides. So we have the integral of dy over y is equal to the integral of k dt. So this integral of 1 over y dy would be the natural log of the absolute value of y. And then the other side would be k times t plus c. And now I would like to solve this for y, so I get a y equals equation. So I'm going to raise both sides to the e power or exponentiate to get rid of the log. And remember, the plus c was arbitrary, but if we're raising both sides of the equation to the e power, then the plus c has to go up in the exponent. This side, the natural logs cancel, so I get absolute value of y is equal to e to the kt plus c. And then I'm going to remind you of an exponent property, which is e to the a times e to the b is going to be equal to e to the a plus b. That is the product rule for exponents. So I'm going to change this sum of exponents to a product. So I get absolute value of y is equal to e to the kt times e to the c. And that is product for exponents. And then I'm going to rewrite this so it's y is equal to plus or minus e to the c times e to the kt, because I know that after I take the absolute value, I know that the value is positive, but I don't know whether the value is positive or negative before I take the absolute value. So then We're almost there. We just have this messy plus or minus e to the c. So we're going to give that a name. We're going to call it p. Let p equals plus or minus e to the c. And so if I rewrite this equation, I get y is equal to p e to the kt. And that sure looks a lot like y equals PERT. We're just using K the way we used to use R when we first learned about that. P, remember, is going to be our initial amount. And so that is the exponential growth equation, which is equivalent to this differential equation. Exponential growth or decay. If K is positive, then this would be growth. If K is negative, then this would be decay. Here it is in formal math language, if you would like the formal math language. If y changes at a rate proportional to the amount present, and you've got an initial amount of p, then y is equal to p e to the kt, which is the one that you're familiar with from intermediate algebra. K is a growth constant, so if k is bigger than 0, or a decay constant if k is negative. All right, here's a situation that I hope sounds like exponential growth to you. At the beginning of the summer, the population of hornets in a hive is growing at a rate proportional to the population. Okay, so in language, that means dy dt is equal to k times y. There are 10 hornets on May 1st. 30 days later, there are 50 hornets. How many days after May 1st until the population reaches 100? All right, so since the differential equation is proportional, we could either go through the whole process, or we could say, hey, when I see that, I know that I have a PERT situation. I'm going to call May 1st. I'm going to call that t equals 0. And so when I fill in t equals 0, I get 10 hornets is equal to p e to the 0, because t is equal to 0. So that means that p is equal to 10. And then it says 30 days later, so I'm going to call that t equals 30. There are 50 hornets, so we'd have 50 is equal to 10 e to the kt. I can divide by 10. Oops, I forgot to fill in the 30 for t. And then I'm going to take the natural log of both sides. So my growth constant is natural log of 5 divided by 30. And so this is my full equation for these murder hornets. And how many days until the population reaches 100. So I want to figure out y equals 100, what does t equals? And this is a graphing calculator question. So I'm going to let you grab your graphing calculator and find that solution. I will also do it, but I don't have a graphing calculator at home, so I'm going to use Desmos. So we have, here's the equation, and then we have a second equation, which is y equals 100, and we find out where those two equations cross, and it looks like it's 42.92 days. All right. Here's another example. Scientists who use carbon-14 dating use 5,700 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. Okay. So Carbon-14 dating, that's an exponential decay situation. So dy dt is equal to k times y. Oops. Which again means y is equal to and then we're going to do that 55,700 years is the half-life. So if I say, we're going to say, t is equal to that many years. And if we start with p as the initial amount, since this is the half-life, we would have 1/2 of p. So I'm going to rewrite this. So I have 1/2 p equals p e to the 5700 times k. Divide by p, and I get 1/2 is equal to e to the 5700 times k. And we're going to natural log both sides and divide by 5700. So we have natural log of 1/2 is equal to 5,700k. And then divide. So this k is a negative value. And so this is the equation we have for this situation. And if I want to know how old a sample is in which 10% of the nuclei have decayed, 10% would be 0.1 times p. So I'm going to rewrite this as 0.1 p. Divide by p. And then log both sides, or grab your graphing calculator and use that to solve for t. So here's my Desmos graph of this situation. You really have to play with your scale in order for it to look exponential, and I used a scale of counting by 5,000s here, and so I have I changed my window so that it would be big enough to see. So it would be 18,935 years old. So that's exponential decay. Really, you have to be comfortable with that PERT equation and using it to figure out what the k is with kind of two data points, and what p is, which stands for the initial amount. All right, good luck.